Welcome to Ideas on Tap, presented by the Museum of Natural and Cultural History. I'm Lauren, and I'd like to start this evening by recognizing that the museum and the University of Oregon are located on Kalapuya Ilhi, the traditional indigenous homeland of the Kalapuya people. We recognize and honor all indigenous people who continue to call the Willamette Valley home. If this is your first Ideas on Tap, welcome. Although we might not be together in person, we do still want to hear your questions and your comments. You can use the Q&A or chat feature on both Zoom and Facebook to ask questions of our speaker, to reflect on the talk, or to engage with other viewers. I'll be collecting your questions across both platforms, and we'll get to as many as we can at the end. I want to give a quick shout out to our friends over at Viking Beer Company, who, pre-pandemic, hosted the museum's Ideas on Tap program at their Southtown location. I saw this morning that today is apparently National Beer Day, so I hope that some of you were able to pick up some braggot to go before joining us this evening. During the talk, I'll post a link to a brief survey in the comments on both Zoom and Facebook. I'd appreciate it if you could take a minute or two to fill it out, as your feedback will help us improve future virtual programs, and you'll be entered to win a $25 gift card to Viking Beer. If you enjoyed tonight's program, we are asking that you please consider making a secure, tax-deductible donation of $5 to $10 at the web address listed on the screen to help keep museum programs like this one accessible to all. That's giving.uoregon.edu/MNCHgift. Your donation directly supports the museum's educational programming, bringing science and culture adventures to Oregonians of every age and in every corner of the state. Thank you. Finally, I hope that you'll join me next month for another Ideas on Tap. On Wednesday, May 5th, UO music theorist Drew Noble will discuss the chorus in rock and pop songs and how it has evolved since its emergence in the 1960s. It will be our last Ideas on Tap before we take a 3-month break for the summer, so don't miss it. But if you can't join us live, we will post a recording to the museum's YouTube page the following day, so be sure to check it out. And now it's my pleasure to introduce this evening's speaker, Dr. Dave Sutherland. Dave is an associate professor of earth sciences at the University of Oregon. His research interests include coastal and estuarine oceanography, as well as ice-ocean interactions. In particular, his work focuses on the dynamics of glacial fjords and Pacific Northwest estuaries, and how humans interact with these environments. He joins us this evening for a discussion about the iceberg life cycle and how Greenlandic iceberg melt is affecting global climate. Welcome, Dave.
Thank you, and thanks for having me. And it's really an honor. I didn't realize it was National Beer Day, so that makes it an extra special Ideas on Tap, I think. So right. Thank you, Lauren, and thank you, Andrea, too. And thanks to the museum for hosting this event. I'm going to go ahead and share my screen so you all can see some of the pictures that I want to share with you tonight. As Lauren said, I'm going to be talking about Greenlandic icebergs. And I know for some of you, you might know what an iceberg is. For some of you, you might not know what icebergs are. And so I think my biggest goal for tonight is just to give you a sense of the beauty of these icebergs and a little bit of how they form and why they're important, and why I study them, really, why I spend years of my life studying these icebergs. And so what you're watching here is a video clip. It's on repeat of icebergs actually forming from a glacier in Greenland. And so the glacier is on the right, over here, and this big iceberg just calved off the glacier into the fjord. So underneath all this ice on the left is actually ocean water, fjord water. You just can't see it because there's so much ice. And we say calved because that's literally what they're doing. They're breaking off the glacier, and it looks like when people first described the process, it looked like the sort of the calving of a whale. And so we tend to call the process iceberg calving, and all that means is a breaking off of ice from a glacier. And this is distinct from sea ice. So if you're thinking about Arctic Ocean sea ice or sea ice in the Antarctic around in the Southern Ocean, that's ice that forms out of the ocean water itself. Here we're talking about icebergs, which are freshwater. And so these are pieces of ice that float in the ocean that come from land. Okay, so these are land ice pieces that then go into the ocean. All right, as you can tell, you get a whole range of sizes of icebergs around Greenland, and we'll talk about why that's important moving on. Okay. Some of you might have seen icebergs if you've been on a cruise in Alaska, or if you're really lucky, maybe you've been on an Antarctic cruise and gone down to the Southern Ocean. And so the other part I want to do tonight is just give you a sense of the scale of what these icebergs really are, and sort of the grandeur of them. But really, when you think of icebergs, I'm sure the first thing you think of, obviously, is the Titanic. Hopefully, many of you have seen this movie. If not, you've, I'm sure, heard of the Titanic, the disaster that happened in 1912, when that large ship ran into this iceberg. So this is the picture of the purported iceberg that took down the Titanic. It's about a 100-meter, 300 feet long iceberg. This is the paint. If this was a color picture, this would be red paint from the hull of the iceberg. And so a fairly small piece of ice took down the greatest ship, of its time. The silver lining, of course, was that this led to the creation of this International Ice Patrol. So this is a group that now patrols the northern North Atlantic and looks out for icebergs and provides real-time reports on iceberg hazards to shipping and to oil companies that now have oil platforms off the coast of Canada and in the future off the coast of Greenland, most likely. And so icebergs, are a hazard, and we know that from the Titanic. And we've been mitigating that hazard and learning a lot about icebergs since, over 100 years ago. You might have also heard about icebergs if you've ever seen this famous Italian singer. You can look this guy up on YouTube. He floated on a homemade iceberg in front of a actively calving glacier. Not something I'd recommend, but he played some nice music and got a lot of money for Greenpeace. So there you go. Third, and maybe closest to my heart, is why we think about icebergs in terms of science. And the first thing that comes to mind is probably climate change, right? When you think about icebergs, your mind instantly goes to catastrophe, to calving glaciers, to these icebergs just, sort of being an icon of loss of global climate change. And this is a picture of a really large glacier in northwest Greenland called Petermann Glacier. And what you can see here, the glacier is down here in the bottom of the picture, and it's flowing into the fjord. So it's flowing up into this picture. This large piece of ice right here is actually an iceberg, and it's large enough that we'd actually call it an ice island. So this fjord itself turns out to be, if I annotate this width of this fjord is about 15 kilometers, or about 9 miles wide. Okay, so this ice island right here is about 9 miles wide by about 15, 20 miles long. So this is an enormous piece of ice that just broke off Petermann Glacier. Right? And so when you think about that, instantly it brings to your mind like, oh my gosh, the Greenland ice sheet is losing all this ice. Icebergs calving into the fjords is just a sign of global climate change. And we know, and I'll get into this later on, but that's not entirely true. Iceberg calving is a natural process. But when mass loss or ice loss from the Greenland ice sheet outpaces how much snow it gets, then that's a problem. Okay, and we'll talk about other scientific impacts on the global ocean. Okay, if you're a glacier that calves off a piece of ice into the ocean, you're actually raising sea level by a little bit. Okay, when that iceberg is then floating in the ocean and it melts, that doesn't raise sea level anymore, right? You can do an experiment if you have a drink at home with ice in it, right? As that ice melts, your drink doesn't overflow all of a sudden, right? There'd be a lot of problems at restaurants if all of a sudden when the ice melted in your tap water, if it started overflowing. Okay, so floating ice when it melts doesn't raise sea level, but when these icebergs calve off glaciers, they do raise sea level. And so that's really one of the major concerns of why people are studying icebergs and the amount of icebergs being discharged by the Greenland ice sheet or the Antarctic ice sheet. But there's numerous other impacts. Okay, so this is the only plot I have in this whole talk, so you got to bear with me a little bit here. It looks complicated, but I'll walk you through it, okay? I like data plots, and so I hope you do too. I'll try to walk you through it here. So what we're looking at here is actually a measure of the cumulative ice loss from Greenland. So this is how much ice is lost starting in 1972 and going to 2020. All right, in the purple line, you see here, so it starts at 0. In the purple line, this is showing you the total loss. Okay, so if it hovers around 0, that means the Greenland ice sheet isn't actually losing ice every year, right? So it's gaining as much ice as it's losing. There's a 0. It's like if you put in your bank account $10 and you take out $10, you know, your net is 0. Okay, so the first few years here, the first decade, you're around 0. And you can see we've entered this really rapidly accelerating trend where the total mass loss now is hundreds of gigatons per year. Okay, so let me just orient you on what's plotted along this axis, right along the y-axis. This is thousands of gigatons lost, so thousands of gigatons. So the 5 here is actually 5,000 gigatons. A gigaton is 1 billion tons. Okay, so that's 1 trillion kilograms, or about 2.2 trillion pounds of ice. So that's a lot, right? And so what we're saying here is the total mass loss since 1970 is about 5,000 gigatons of ice. That's ice that is put into the ocean, right? Which is why it's about 15 millimeters of sea level rise. If you spread that ice, if it melted and you spread that around the global oceans, you'd raise global sea level by that amount. Okay, but what this plot does that I like, it actually breaks it down even more. So from Greenland, you can break it into 2 parts, right? So Greenland is losing ice either via icebergs, right? It's calving off this solid pieces of ice. And that's what the red line is. It's also losing ice through melting, right? So in the first part of the latter part of the 20th century, right, you can actually see this as a positive number. So Greenland was actually gaining snow in those years, okay? But it was losing more through icebergs, so the net loss was negative. Okay, but in recent years, it's not been snowing. It's been melting on the surface of the ice sheet more than it's been snowing. So now we're losing mass both through iceberg discharge and through melt on the surface of the ice sheet. And that's led to some really large input of fresh water into the ocean. Okay, and this is one of the prime motivations for why people want to study Greenland, Antarctica. In particular, for me, it's interesting because most people just want to focus on this. And once the iceberg calves off the ice sheet, they kind of forget about it. Glaciologists, people that study the ice, just say, okay, it's not part of the ice anymore. Let's just forget about the icebergs now. And from the ocean side, like icebergs aren't ocean water. And so oceanographers like myself don't really study them either. And so I often characterize icebergs as kind of like that forgotten middle child between oceanography and glaciology that no one really studies them. It's like kind of a lost part of the climate system, even though we know they're really important. Okay, beyond sea level rise, which I was talking about in this data plot, okay, icebergs actually are an interesting way to move fresh water from right next to the ice sheet way out into the North Atlantic, right? That iceberg that hit the Titanic, it was really far away from the glacier that it came from in Greenland, right? It moved all the way down into the northern North Atlantic Ocean. So icebergs are this interesting thing that can move fresh water around the globe. Okay, as we also saw, they're shipping and infrastructure hazard. They also create their own ecosystems. In the Southern Ocean, they're particularly good at inputting iron, and that acts as fertilizer for the ocean, right? It's a plant fertilizer, it's a plant nutrient, and all of a sudden you get these blooms of phytoplankton that follow icebergs around. And then finally, you might have heard, a year or two ago, South Africa was seriously considering using icebergs as a water resource. This has been done maybe every 10, 20 years. People bring this up and think about, oh, should we use icebergs as a water resource? And inevitably, it always gets shot down for some reason. But someday it might make sense. Okay, so I've talked a little bit about why I think icebergs are important. But again, I don't think I've really conveyed the scale yet of the iceberg. So I'm going to show you a short movie here. Okay, where you're looking at, these are some icebergs in a fjord. So underneath all this is water. This thing right here where the pointer is looking at helo is actually a helicopter. It's a Bell 212 Air Greenland helicopter. Okay, we were in there taking measurements. So we're lowering a sensor down into the water. This is the water right here, this patch. And I'll just play the movie now and you'll get a sense of the scale. If you can, try to keep your eye on the helicopter. It's going to zoom out. All right, so if anybody can keep their eye on the helicopter the whole time, you win the prize for the day. So far, so good, right? It's still here. It's still there. Still zooming out. I kind of lost it. All right. So this gives you a little bit of sense of the scale, right? That helicopter is maybe the size of 2 large cars, a couple big SUVs maybe. But when you zoom all the way out, you see the scale of all the ice that's being put into this fjord by the glacier that's just off screen here that you can't actually see. And there's a whole host of iceberg sizes, right? There's large ones, there's small ones, there's medium ones. And that's important because those icebergs actually melt and move at different rates. And so we want to be able to characterize the shape of these icebergs. And so the first lesson for today, I'm going to give you 2, maybe 3 takeaways for today, is that size matters. Okay, when we talk about icebergs, iceberg size matters, right? When you're looking at this picture here from that same fjord I just showed you, this is a fairly large ship. Okay, but you can see these icebergs. There's small ones, there's big ones. This iceberg off in the distance is actually a tabular berg. This is an iceberg that calved off a glacier or didn't flip over. Okay, it actually still looks like an iceberg. Still looks like the glacier on top. And this iceberg in particular is maybe about 2 kilometers long, so a little over a mile. And I tried to think about, okay, how much volume, right? This is just the tip of the iceberg too, right? So the amount of volume in this iceberg, if you think about some amount of volume, say in your favorite football stadium, right? Maybe Autzen Stadium, maybe Reser Stadium, or the Coliseum if you're from LA. This iceberg would fill up about 500 of those stadiums. Okay, so there's a lot of ice in this iceberg, even though it doesn't really look like it, right? Imagine it goes down about 9-10 times deeper than what it looks like here. All right, so these icebergs are massive and they carry a massive amount of fresh water with them. And that's really one thing that we do in my lab. And so I haven't really introduced myself, but as Lauren introduced me earlier on, my name's Dave and I'm an associate professor in the Department of Earth Sciences. And I come from an oceanography background, but I've really gotten interested in the questions that happen at the interface between ice and the ocean. So be it icebergs or glaciers, I like to study those places where those meet the ocean. And we study icebergs that, that also carry sediment, like this iceberg here, which is very dirty and sending off plumes of sediment. And I particularly like to just acknowledge my lab group and the students and postdocs that work with me, because they're the ones that really do the work. I sit back and write papers and proposals and things, but they're the ones going out there and collecting the observations, doing the analyses, and actually doing the real work. And sometimes it's not as glorious as it looks in this picture. Oftentimes it's wet and cold, and you have to be on deck, kneeling on a metal deck, trying to finagle a little piece of hardware into a sensor or a mooring, which is what we're doing here. So we collect oceanography measurements. We also use simulations and sort of math and theory to think about how icebergs move and melt in the ocean. But I'm not going to get into too much of that today. I'm going to give you more of a high level picture. And first, I want to start with the Greenland ice sheet. So this is kind of a primer on how ice sheets work, okay? In the middle of the ice sheet here, depicted in green, you have snow accumulation, right? And as that snow builds up year after year, it compresses and it gets thick enough that then the ice actually flows under its own weight. And that's what a glacier or ice sheet is, right? It's just ice that's moving under its own weight. So there's been so much snow accumulation that turns into ice flow and it moves toward the edges of the ice sheet. Okay, so, but on the edges, right, if you just had snow accumulating, your glacier or your ice sheet would just continually grow. Okay, so there's ways that it actually loses mass. So we have surface melting, right, and that's what we call ablation. Ablation is just a fancy word for surface melt. We can have subglacial melting, that's what happens underneath the water. And then we can have iceberg calving, which are these big chunks of ice calving off the ice sheets here. So if these 3 things balance the amount of snow you put on top, then your ice sheet is at steady state, right? It's not changing. You gain some snow, you lose some ice, and overall, the mass of the ice sheet stays the same. Right? But what's been happening in recent years is that these losses have far outpaced the gains of snow we have, right? By thousands of gigatons. Okay, so it's not a small imbalance, it's a very large imbalance. And one thing I just want to point out, since this is a talk about icebergs, is how this figure actually comes from a textbook. And the textbook is very poorly drawn icebergs here. And I just want to acknowledge that and show you a cool website. So why are they wrong? Well, I'm going to go to this website and I'm going to draw this iceberg shape and you'll see why they're wrong. So let me just show you. So hopefully you can see this website. This is a cool website called Iceberger. I encourage you to go check it out. You can spend a lot of time playing with this. If we draw what that iceberg looks like, that we just saw in that schematic, and we let it go, it's going to float how a real iceberg would float. And it doesn't look anything like the iceberg in the picture, right? In fact, it's going to tip over, and it's going to want to find a more stable position. Okay, so the icebergs that you see depicted often that are really long and skinny and tall often aren't very realistic. Okay, icebergs that we see in nature are more like this, or even, I'll show you later on some real pictures of icebergs, or even things like this, right, that have much more massive pieces underwater, but they're not like these long skyscraper type icebergs. All right, so I encourage you to go play with Iceberg after the talk. So let's go back here. All right, so that's a primer on the ice sheet. I've shown you a lot of pictures so far of icebergs. So what's been the theme so far in all the images I've shown? Give you a second to think about that. Well, they've all been from above water, right? I've only shown you pictures of icebergs from above water, because that's, obviously that's a lot easier to get pictures of icebergs above water, right? We can take drones, we can take planes, we can take satellite pictures. If you've ever flown from the Northwest to Europe, you've probably flown over Greenland and seen the ice sheet, and maybe even seen icebergs. Right? It's very common to take that route over to Europe via Greenland. And so it's one of my favorite things, actually, is you look out the window and it's the middle of the night and you look out and you see Greenland, and it's just amazing. But okay, so remotely sensed, I've only been showing you above water pictures, and that's a problem, right? Because we know that most of the iceberg is below water. So that's lesson number 2. Okay, underwater shape matters. All right, I'm going to show you why. I'm going to tell you why, and I'm going to show you why with a little science experiment. And then I'll do this science experiment. We're going to let it sit for a little bit, and we'll come back to it at the end of the talk. All right, so let me see if I can stop sharing for a second, and I'm going to switch over to a different camera. This is still me. Here's my hand. Hi, everyone. Okay, so what we're going to do here is a little science experiment. I've got 2 jars. I'm going to put some water in each jar here. Looks good. I have another water bottle, don't worry. All right, let's see how those look. They look kind of equal. They look kind of equal. I'll put a little more in each one. Okay, good. All right, so what we're going to do is think about how icebergs melt. We're going to do an experiment where we put icebergs in fresh water versus salt water, right? Because what's the ocean? The ocean is salt water, right? And so I have my instant ocean here, right? Salt. Okay, so we're going to make some salt water. We're going to make some ocean in this one right here. Let's pour in some salt. There we go. That's exactly how much you need to make an ocean. Stir it around a little bit. Okay, everyone remember that this one on this side. Here, I'll put a little sticky note here. The one with a sticky note, all right, is our salty water. This is our fresh water, all right? And now I've got some ice here. I'm going to put in each one. I'm going to start putting it in. We're going to make our little iceberg melange here that you saw in the other pictures. I don't have quite the scale of icebergs maybe that they have in the pictures, but it's going to do the trick. Let's see here. Let's keep going. What do you think? A little more? Which one needs more? How does it look on the picture? Ooh, this one needs more. There we go. They look pretty good. Okay. One more. Okay, so our experiment here, and what I want you to think about at home, is in which jar, in the ocean or the fresh water, so ocean water, fresh water, in which jar is our iceberg melange, our mixture of ice here, is it going to melt faster? Okay, so make your prediction. Is it going to be the salt water? Is it going to melt faster in salt water? Is it going to melt faster in fresh water? Or maybe they're both going to melt the same. That's the third outcome. Okay, we're going to let them melt a little bit, and then we'll come back and test this experiment and see what the results are and talk about it a little bit. It's going to let us talk a little bit about salt and what makes, why that's important in the ocean. Okay, so I'm going to go back to my screen share here. And back to this. Okay, so I said underwater shape matters, right? And I say that because we don't have a lot of measurements. We don't have a lot of observations of underwater iceberg shape. In fact, when we, in global models, and I say models here, I mean like a simulation that we use to think about global climate, that we use to make sea level rise predictions, right? We have these simulations that predict what the ocean does, what the atmosphere does. And they actually are starting to include icebergs in them, believe it or not. But the icebergs they use are very idealized in the sense that they look like a block, they look like a cone, sometimes they look like a cylinder. You can see that these are all very sort of simplistic views of what an iceberg might look like. And it's important because if you put the same volume of ice in these three different shapes, they actually reach down to different depths in the ocean. And that actually is significant and plays a big role in how they melt and they move. Right? You can imagine that the ocean currents at the surface are different than down here deeper. And so they might move differently if they reach different depths. And it turns out the temperature of the ocean is not uniform, right? So the temperature of the ocean varies with depth. And I'll show you that in 1 second here. So that's one reason shape matters. Another reason why shape matters, you might be asking yourself, okay, why does shape matter again? He just told me, but I forgot. I'm going to actually go back to my origin story and tell you a little bit about where I began. I grew up in North Carolina, sort of right here. And what I'm showing you here is a picture of the Gulf Stream and the ocean currents. So what the Gulf Stream does is it brings warm subtropical water from near the equator up into the North Atlantic Ocean. I did my graduate school here in Cape Cod in Woods Hole, again, right next to this Gulf Stream that is bringing heat up from the subtropics and then across the ocean towards Europe, but also you can see it kind of has this northerly tilt, right? So the Gulf Stream actually turns into a current that we call the North Atlantic Ocean. The North Atlantic Current. And that North Atlantic Current bifurcates. Some of it goes towards Europe. Some of it actually turns north and goes up past the UK, up towards Scandinavia. All right, and the other thing I just want to point out about this picture, why I love it so much, is that it really depicts what the ocean looks like in terms of these cyclones and the weather that we get in the ocean. Now, the ocean is almost like the atmosphere. There's oceanic weather, right? If you live in the ocean, you get a weather forecast and say, oh, here comes a low. Here comes another high pressure system. We just don't have that. No one's really demanding that yet. There's no big communities that are out in the ocean, but it's going to come someday. All right, so that North Atlantic current that I was just depicting here, this is another schematic showing you. It comes up from the subtropics, and here it is shown. It goes up by Norway and into the North Atlantic. Sorry, everyone. But part of that North Atlantic current actually turns left and goes toward Greenland. So here's Greenland, right? This big piece of ice right here. And I'm telling you this because that water is relatively warm, right? The Gulf Stream is, 20 degrees Celsius. By the time it gets here, it's more like 10, 12 degrees Celsius. By the time it gets over by Greenland, it's like 4 to 6 degrees Celsius. But that's really warm, actually, compared to the Arctic Ocean waters that come down from the Arctic and that hug the coast of Greenland. And so right around Greenland, you get this mixture of really warm water and really fresh, cold water. Okay, the North Atlantic current turns out to be really salty. So it's salty, warm water and cold, fresh water that mix right around Greenland. And that's really important. Okay, so what that actually means is when you look at an iceberg, so you can ignore the little M's here, but just look at this iceberg, right? We've got a surface part, we've got a part deeper. On the right, oh, actually I lied. I have one, this is the second plot that I'm going to show you. Sorry about that. But this one's a little easier. This is 0 meters means the surface. So here we are at the water line. And as you go down, you're getting deeper in depth, right? So we're going down to 500 meters here. What these lines actually show are temperature. So as you go down in the water column, as you go down, as you go deeper, 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 the temperature actually is increasing, right? And that's because it's actually getting saltier as you go down, okay? Typically, we think about the opposite way, where it's warmer at the surface and it gets colder with depth. But here in the Arctic, in the subpolar regions, it actually gets warmer with depth. And so if you're an iceberg that's 100 meters deep, you're experiencing water that's a lot different than if you're an iceberg that's 500 meters deep, right? You're in a very different type of water. And that might affect your melt rate. It might affect how far you make it away from the Greenland ice sheet before you break up. Okay, so again, we have cooler water at the top, warmer water at the bottom. Okay, and this is something we have to take into account when we think about iceberg shape. All right, when we think about iceberg shape, I want to show you some real iceberg geometry. So I showed you those ideal ones, simplistic ones before. Here's 10 real iceberg geometries that we gathered data from in Greenland over the last couple of years. Okay, so you can see the water line in all of these pictures is sort of this gap. You can imagine that the water is there. So there's a surface expression. So this is above water. And all this stuff that you see below, that would be below water. Okay, I'll explain in a second how we get that imagery. Okay, but what I want you to take away is that these iceberg shapes are all very complex. There's ones that look like cones, kind of. There's ones that have, expressions that go out from, if the iceberg actually extends way beyond what it looks like at the surface. Okay, those are the scary ones. That when you take a ship over it, you realize that your ship is actually over top part of the iceberg. All right, and so this set of icebergs, we've got about 10 others, represents kind of the state of the art and the most detailed iceberg geometries we have in the world right now. And this is done by a postdoc of mine named Kristen Schild, who's now at the University of Maine. All right, and how we collect this data. So I'm going to show a little movie here. Is we put together GoPro, right? That's just a camera, and some drone photos. So we take thousands of photos. And then we also have something called a multi-beam sonar. A sonar is, you think of it as a fish finder, just a fancy fish finder. And this multi-beam part just means we get a swath. So we get millions of points. Every time a sound pulse goes out, it hits against the ice and it comes back. And we can measure that distance. Okay, and as I show you this movie, what you can see as we go around this iceberg, this is sped up a little bit. Our boat is not going this fast, but as we go around this iceberg, we're collecting imagery above the water, but we're also collecting imagery below the water. And we can put those together to make some of the first fully 3D geometries of icebergs that then we'll get to use for all sorts of fun science. Okay. And this is a particularly clear, sometimes there's a lot more ice around these icebergs and we have to be more careful. But this is pretty open water. But you can see that the shape under here, so the colors just represent depth. Again, the red is shallower than the greens and blues. But we take all these photos and we actually stitch them together in a process to actually create like a topographic map of that iceberg. So we can actually have these 3D renditions of icebergs. All right. And this is what they look like. Again, I showed you a different version of this earlier on, but just I put some dimensions here just to show you how big these things are. So here's some of the icebergs we collected data on. 700 meters long, about 400 meters deep. So that's almost a kilometer long, half a mile wide, versus 1,200 feet deep. And we do some smaller ones, even though our smallest one here is still 80 meters long, 200 feet long. Okay, we can take these and we can think about if we take repeated measurements in time, right? If I showed you these imageries and then we said, oh, let's go back in a week and do it again, we can actually directly measure how those icebergs melt. And that's really powerful because that allows us to say something about the process of melt. And so we're studying these icebergs in one fjord in Greenland, but then we can say something more general about icebergs anywhere because the same physics applies to icebergs if you're in Greenland, if you're in Alaska, if you're in Antarctica, if you're in Patagonia, wherever these icebergs are forming, we can talk about melt in a more general way by what we learn in this project here. Okay, so first lesson was size matters, right? But we can learn a lot about size from space, from satellite imagery, also from drones and your own cameras. But underwater shape matters just as much. Okay, if we want to understand how icebergs move and how they melt and how they might impact, say, a ship or an oil platform or the North Atlantic Current or the Gulf Stream, we need to understand where they go. And to get that, we need both of these. So we need size and we also need their underwater shape. All right, and I'll just reiterate, though, that icebergs are a natural phenomenon, right? So when you see an iceberg, don't immediately go to climate change. But what it should remind you of is that, okay, but if that ice discharge from Greenland is a lot more than the snow accumulation, then yes, that is a big problem. And it is, I will certainly admit and certainly push that it is alarming how much ice Greenland and Antarctica are losing each year right now. It's not sustainable. And we're about there's debate in the science community, but we're reaching kind of a threshold or a tipping point where there's not a chance to go back after that. And I haven't forgotten our science experiment. So let's go back to that and see if we can learn anything there. So I'm going to stop sharing. Hopefully you can see my hand here again. Okay, so let's go back here. So, all right, so this is the salty one. Remember, salty one here. Here's our fresh one. Okay, did everyone have their prediction in mind? So what we're going to do to visualize this, I have some food coloring, red. I'm going to put some food coloring in each one, and we'll see which one is melted faster. Actually, you can kind of see it maybe already, right? Maybe it's hard to see. I probably didn't allow enough time to go for this science experiment, but it almost looks like the freshwater ice is a little bit more melted than the salt water. And let's figure out why that is. So I'm going to put some dye in the fresh water. One here, and see if we can see what happens. I'm not going to stir it. So what do you see? Well, you see food coloring going to the bottom, right? You can see it sort of circulating around. It's sinking to the bottom. So that says that there's some sort of circulation in that jar where water is moving towards the bottom. Okay. Even if you account for some of the dye, like was heavier, there's still movement happening way after I put it in. Okay, contrast that with what happens in the saltwater one. All right, I'll do one more. Okay, we'll wait a second here. Wait for the dye to sink. Oh, wait. It doesn't actually look like it's sinking. Okay, so what's happening here? Let me push it down. I'll try to push the dye down. See what happens. Nope. All right, so since I can't actually interact with you live, I'll just have to tell you what's happening. Okay, in the freshwater jar, I put water in here. The ice was colder than the water. So as the ice starts to melt, cold water is more dense than warm water. And so that creates out this little convection cell. Okay, so that cold water sinks, warmer water is brought up, and you actually enhance the melt rate of this. Okay, so in this sense, we actually get more melt in the freshwater jar. In the saltwater jar, right, it was warmer, but it was actually saltier. And salt makes water more dense. Okay, so the fresh water that melted from our ice actually just sits up there and creates this fresh layer of water. And so when I put the dye in, it all sits in that upper layer. In fact, I can't even force it down, right? We can kind of create little internal waves here at the interface between the fresh water and the cold water. So it's like the icebergs here are being insulated by that freshwater layer. And so this lets me talk about the ocean being what we call stratified. So the ocean is less dense at top and gets more dense as you go down. Okay, and so that stratification is also another factor that we have to take into account when we think about melt rates of ice itself. All right, so hopefully your predictions were right. Maybe you guessed this from the get-go. I hope so. I'm going to go back to sharing really quick. I'm almost done here. So that was a science experiment. If we could play with this experiment and actually put in bigger ice cubes, smaller ice cubes, and really show you that size matters too, but in the interest of time, we'll just keep moving on. The last thing I want to share is really, I said a bunch of reasons at the beginning about why I study icebergs, but really the ultimate reason is that I think they're beautiful and they kind of take my breath away when I get to go out in the field and be around them. And I thought this movie was a great illustration of that. It comes from the mouth of the Ilulissat Ice Fjord. So Ilulissat is a UNESCO World Heritage Site in West Greenland. And you can walk down, and we're in a boat here, but you can actually walk down to this spot and look out and see all these icebergs that are parked at the mouth of the ice fjord here. So the glacier is about 50 miles into the distance here. And it pumps out enough ice that it fills this whole fjord with large icebergs. And what happens, why there's open water here, is that there's actually an underwater submarine mountain that blocks these icebergs from passing until they get to be a certain size, and then they can exit the fjord. But if you see on the very edge of this picture, here's the town over here. And it's just an amazing spot you can go to and walk out to the edge of the fjord and look at these icebergs. And so I think they're just beautiful, and we're still learning. I mean, we're still learning really basic things about these, right? Like the fact that we didn't know their underwater shape to such a detail was really surprising to me when I started 10 years ago. And so we're just kind of still making kind of discoveries about icebergs, and that's the kind of science I like to do, is really exploratory and discovery based. So I will end there, and I thank you for your time and your attention, and I'm happy to answer any questions now, or get in touch with me after this if you want. Just email me. I'm always happy to chat. So thanks so much.
Thanks so much, Dave. That was great.
I'll stop sharing. Yeah.
I love the science experiment.
Mm-hmm.
I had actually done it before, so.
You knew. You can see it. It's still there.
I will admit, the first time I did it, I predicted they would melt at the same rate. So I did not have a correct hypothesis. So far, we only have a couple of questions coming in. So I just want to remind people that you can put your questions in either the Q&A or the chat if you're on Zoom. If you're watching on Facebook, you can put it in the comments, and I am checking that as well. So we'll go ahead and start with the few that we have. Someone is wondering how solid icebergs are and whether cavities within the icebergs can alter how they melt.
Yeah, that's a really good question. I see that question in the chat. Thanks, Ethan. Yeah, so since icebergs come from glaciers, they have about the same density of ice that land ice has. So that's about, so water, fresh water is about 1,000 kilograms per meter cube. Ice is about 9/10 of that, which is why it floats, right? So it's a little bit less dense. But importantly, icebergs actually change their density as they age, right? A fresh iceberg that just calved off the glacier will be just as solid as the glacier was. But as it melts and moves through the ocean, you do get a lot of air pockets and melting and dissolving, and even from the surface too, right? That solid ice will turn into snow and fern and mushy stuff. And so it becomes less and less solid over time. Yeah, so that's a really great question.
Thanks. Someone is wondering what kind of animal life lives on icebergs.
Yeah, that's a really interesting question, actually. So icebergs are used there's two things. But if they live on the icebergs, that's one thing. Icebergs also create a lot of mixing and stirring up of the water column that actually generates a lot of life around them too, in their very close proximity. So first of all, around Greenland, it's known that polar bears will actually use icebergs to move up and down the coast, which is pretty remarkable to me. But they've actually found, in particular, polar bear moms will make their dens on icebergs, and they're apparently very good at picking nice, big, stable ones that won't break apart. So polar bears, seals will use icebergs, much smaller ones, to haul out on. They use sea ice as well. So anything that floats, they'll haul out, and spend some time on icebergs. And then the marine ecosystems around them are just diverse, right? Because they go from phytoplankton all the way up to whales. So you can have the whole food web around an iceberg. And in fact, we often, at that last video I showed you at the mouth of Ilulissat Ice Fjord, there's often humpback whales that just sit there and feed because they know it's such a rich, diverse ecosystem.
Very interesting. I've did some traveling in Alaska and was able to see some of the animals around the icebergs and glaciers. So it's really cool. Yeah. Someone is wondering whether icebergs move along with the currents at the same speed as the currents.
Yeah, that's a good question. So it depends on the size of the iceberg. So the other thing that can affect an iceberg is the wind. So it turns out for small icebergs, so we're saying like maybe car-sized, or maybe a little bigger than that, maybe building-sized and below, the wind actually is just as important as the ocean current. And so the wind can actually blow an iceberg in the opposite direction if it's strong enough of what the ocean is doing. For really large icebergs though, just imagine how much ice is below water. Those guys, like, they're so massive underwater that they're just moving with the ocean current. But just like the temperature varies in the ocean with depth as you go down in the water column, currents actually aren't all uniform either. So you can have currents that are going really fast at the surface one way, and you have currents that deeper down that are going just as fast in the opposite way. And your iceberg might just be sitting there because overall there's not any net motion. If you took like an average over the whole depth of the iceberg. And in fact, you can see this if you look on YouTube or find some cool iceberg motion movies. You can see icebergs moving in different directions in the same fjord that are different sizes, right? And that shows you exactly what I was just talking about. That the icebergs are getting pushed around by different currents because there's different currents at different depths.
So kind of related to that and related to the experiment that you did for everyone, recently in the news, there's been some discussion that as these icebergs begin to melt, especially like around Greenland, and forgive me if I get some of the details wrong, it could affect how that North Atlantic current moves, and then how warm water is brought to places like Europe, up the north coast of the United States, and that could have a pretty big impact on climate change. But it seemed like there was maybe a little bit of disagreement among scientists about how much of an impact that could have. Do you have an opinion or a
right?
hypothesis?
Yeah, I mean, I can certainly add to that discussion. I mean, if you've ever seen A Day After Tomorrow, right? That's the scenario that they're painting. I can say for certainty it won't happen like it did in The Day After Tomorrow in that movie, right? It won't happen in a day. The Gulf Stream is not going to shut down in a day. But there is evidence that the whole global ocean sort of circulation is slowing down a little bit. And that can be explained by putting a lot of fresh water into the northern North Atlantic, right? So if you're putting all those thousands of gigatons of ice and melt from Greenland, just around Greenland, right? That's putting a lot of fresh water. And as we saw from our experiment, right, that fresh water will sit at the surface. And so you're kind of putting this freshwater cap on the oceans. And what that does is it reduces the amount of overturning or sinking and recirculation of water that happens in the whole global ocean. Okay, it's not happening very fast. And this is where the debate comes in is do we have enough data to even talk about these trends? You need like decades of data, unfortunately. But there is one thing, if you look at, just like we have air temperature going up all over the world, right? Where like every year seems to break a new record. Okay, this is the warmest year on record. This is the warmest year on record. You can look at maps of ocean temperature too, and think about where ocean temperature is increasing, and everywhere in the whole global ocean temperatures are going up as well, except for in one spot, right around Greenland. There's this little cold, blue anomaly, right? If you think of, everyone thinks about red as warmer things, right? Look at these maps and there's just this blue hole right over Greenland. And it's because of all this cold, fresh ice that's getting put into the North Atlantic right around Greenland. So it is a thing. We're still trying to figure it out.
Is that cold water that's sort of now sitting around Greenland, is that affecting how the glaciers are calving?
Yeah, that's a good question. So there are these feedbacks, and that's again where I think the interesting research lies, right? You can study icebergs, you can study glaciers by themselves, you can study the ocean by themselves, but there's actually these processes that feed back on each other, right? If you have more melt, or if you bring warmer water in, you have more melt, and that actually enhances the circulation. That brings more warm water in, you have more melt. And so you kind of get these runaway, what we call positive feedbacks, but they're not positive in any sense. They're just feedbacks that sort of run away. I call them runaway feedback. So, yeah.
So someone is asking about the color differences of icebergs, that sometimes you read about them being green or blue, and what causes those color differences.
Yeah, I mean, the really deep blue, solid, clear blues that you see, those are more freshly calved pieces of ice that have no air pockets in them, or no, there hasn't been any melting yet. And so they'll turn white really rapidly after that. The green parts can be due to a couple things. They can be due to algae that's growing in the water. That actually, this particularly happens around Antarctica. You can get green icebergs. And there, the waters are so cold around Antarctica that you can have something that called supercooling. And on the ice shelves, on the glaciers around Antarctica, you can actually have ice that forms on the glaciers and the ice sheets from underwater. And that will take on a green hue often because it's coming out of the ocean and attaching itself to the ice. So that's marine iceberg, which is a totally wacky but cool thing. So, and then you get a lot of brown, dirty icebergs too, just from all the sediment that's coming off the glaciers. Glaciers are really good at eroding things. I mean, that's, in the Northwest, we should be pretty aware of that, right? Like there's glacially carved valleys everywhere. So.
Right. Someone is wondering if you can tell the age of an iceberg and whether you would classify some of them as fossil water.
That's a good idea. I haven't ever called them fossil water, but yeah, I mean, the age of the water in the iceberg has something to do with how big the glacier is that is calving it off, right? You can have smaller glaciers that are calving into lakes or smaller glaciers up in Alaska that have a really rapid life cycle. So maybe like hundreds to 1,000 years or something like that. And then you can have these systems in Greenland that take tens to 100,000 of years to sort of cycle things through. And so for some of the icebergs, they really are fossil water coming from Greenland in particular. Yeah.
So I believe you mentioned some of your graduate work, and I think you mentioned at Woods Hole. So you might have done some of this, but this person is saying that NOAA does a lot of iceberg research, right? And have you collaborated with them in the past, or do you collaborate with them currently?
Yeah, I would say that NOAA, I have not collaborated with NOAA. And in fact, we've collaborated mostly with, well, there's what I mentioned, the International Ice Patrol. The US part of that is called the North American Ice Service, and that's actually run through the US Coast Guard. So the Coast Guard has a program where people are pilots, right? They go on planes, they survey icebergs, and I can tell you lots of stories of what people used to do in the past of trying to get rid of icebergs. They played a lot of games with icebergs and trying to blow them up, practice their aim and that sort of things. So the Coast Guard is big. And then the Department of Defense actually runs a group in New Hampshire called the Cold Regions Research Lab. And they're part of the US Army Corps. And they are a big group that does a lot of iceberg research too. I'd say those are primarily the federal agencies that we work with. Yeah.
So we don't have any more questions coming in. So we'll go ahead and wrap it up. Maybe if you want to share one more thing, like the thing you think is the coolest thing about glaciers that everyone should know.
Oh boy, that's tough.
Or icebergs, rather.
Or icebergs, yeah. I think, well, I'll talk about glaciers. I'll talk about glaciers that end in the ocean because they birth icebergs. I think when I first started, I didn't think much about animal life. I thought of this as much of a very physical process, right? You think of them as sort of deserts, but then when you go to these places, it's right where those glaciers are calving into the water. Like it's this amazing, like you hear all these noises, snapping, big booms. Like you don't want to be anywhere near that. But then you look and there's a million birds, there's seals, there's fish, there's whales, there's all this amazing life that seems to really thrive right at that interface. And I think that's what surprises me the most. And I think that's sort of the next frontier of this research is like, we got to go beyond the physics, right? Now we can do glaciers and oceans. And then we got to start talking to the biologists a little more and think about how that affects marine ecosystems. So that's the next step.
Perfect. That's a great place to end. If you want to give everyone one more view, maybe of their science experiment and see.
Yeah, sure. Let's see how it's going. Oh, yeah, looks about the same. Yeah, maybe more melt.
Yeah, the melt's becoming much more obvious too.
Yeah. Yep.
All right. Well, thanks everyone for tuning in tonight. Thank you so much, Dave, for sharing your research with us and for giving this talk. We really appreciate it. I hope that everyone is staying safe and healthy. And I look forward to seeing some of you next month back here for another Ideas on Tap. Thanks.
Thank you.